Right, so this work was joined with my student Arun, who has graduated. He's now working at Facebook. So data races. So this is a very important problem. Very long list of papers, PLDI papers, ECOOP papers, just so many of them. So, if you want to summarize them, the various basic models, algorithms for static approaches and Lockset-based algorithms, they are imprecise. And there are a bunch of precise basic algorithms. By basic, I mean they take an event string, including all the a string of events as input, and then they perform race detection. For example, including the classical fast track technique, and also the PLDI 2 days ago, a paper on weakly causal pursuits. So for these basic algorithms, they are precise, but here is the limitation. They are in general slow because they are runtime. They have to check races for each event at runtime. So how about performance of precise data race detection? So this is the problem we want to study. To our best knowledge, so far, the fastest non-happens-before based basic algorithm is the fast track technique. The key idea of fast track is compared to previous happens-before based technique is it introduces a nice insight that can compress the vector clock computation, converting it from ON vector clock operation to, for most of the operations, to O1 epoch-based operations. Here, N is the number of threads. So this was a huge improvement, performance improvement compared to previous happens-before-based techniques. However, it still incurs large runtime overhead. In our experiments, we run the CPU intensive benchmark in the Java Grande benchmarks. We configured with different number of threads. With 20 threads, it incurred 68 times runtime slowdown. So this is without any optimization. So we basically run the benchmarks, run the tool without any optimization turned on in the framework. So here is the question, why O1 is still expensive? The reason is for dynamic race detection, it must check races for every event. Imagine you have a very long running execution with billions of events, and for every event it has to check races. And it has to maintain states, maintain the data structure for checking the happens before relation or epoch-based relation to detect races. So the time complexity remains to be ON. Here, the big N is the number of events. Can we do better? Of course we can. Right? Let's reduce N, reduce number of events. There are, in general, so far, there are two kinds of solutions. One is sampling. Let's sample the events. Right? Every 1,000,000 events, we just check one event for detecting races. So this works well in practice. Right? You can still detect many real races, and it can significantly reduce the runtime overhead. But however, it's still difficult to have any guarantee about the precision or the capability of race detection, because if you miss an event, then you may miss a real race. The second kind of solution is using static analysis. Let's analyze the program first. Let's identify, hey, this statement will never be involved in any events related to data races. Or let's coalesce multiple checks to one event. Right? This actually has been done, for example, in a bunch of work, including the Bigfoot paper recently presented by Steve. So The limitation of these two approaches is races, for example, for sampling, races may be missed. For static analysis, it works for many programs, but for those complicated programs, especially those with dynamic features like reflection, like multi-language systems, it's still very complex. So it's difficult to perform static analysis. So the question we want to ask is, can we reduce the size of events at the same time be both sound and complete? By sound and complete, we mean do not lead to any miss races or false positives. Let's remove an event, at the same time let's guarantee it will not affect the race detection result. So the key idea of our new solution is, let's remove those events that do not reveal any new races. Specifically, in practice, we observe that most memory accesses in real-world program executions are from the same program locations. You have a program statement. This program statement is executed repeatedly in a hot loop or multiple program method calls, and they often lead to the same race because they are caused by repeated execution of the same racy instruction. So here is the main observation. Let's see an example. You have two threads. Each of them run in a hot loop 10 times. The first one has log A, then write to X. The second thread, log B, write to X. Here's a race between 1 and 2. And if you do not have any optimization, the race detection tool will check the events for 1 10 times and for 2 also 10 times. That's 20 times. However, to detect the race 1 and 2, it's sufficient to check only one event for each location 1 and each location 2 and skip all the rest because you found the race. And this optimization, this reduction is tremendous. For example, for SPMD multi-thread programs. So now here comes the natural question. Can we just keep the first event for each program location and then simply remove all the others from the same program location? Can we do this? It is sound? It is complete? No. Let's look at another simple example, slightly changed from the previous one. So you add a notify and wait into the program. So basically you add happens before from some event to some other event across the threads. In this case, the race, it's still a real race between 1 and 2. But however, the race will be missed if we only check the first occurrence, first rise from 1 and 2 and ignore the rest because this happens before from the first event at 1 to the first event at 2. So in this work, we develop a new criterion we call concurrential redundancy. By this criterion, basically we're saying, hey, with this criterion, as long as an event that can satisfy this criterion, then it is redundant and we can remove it safely, soundly, and complete. And then we ask this question, what's the optimal performance of precise dynamic race detection? And we have this hypothetical, this is not real, this is hypothetical. Hypothetically, if all such events are removed with no runtime cost, then the performance of fast track based on the same framework, the same kind of optimization can be improved by 95%. So here is what we found in this work. And of course, to realize this work, we also developed a runtime technique we call REX that can check these such redundant, concurrentially redundant events. And of course, it incurs runtime overhead to find those redundant events. So with this technique, we identified not all possible redundant events. We identified 90% of redundant events, and they improved performance in practice by around 30%. We also have some optimizations I will introduce briefly. Okay, let's start with happens before race detection. Here is the happens before model. You have 5 types of events: memory accesses, including reads and writes to shared memory, the lock acquire, lock release, the message signal, message send, message receive. For example, for Java, if you fork a thread, that's a send operation. If you wait for the termination of another thread, that's a receive operation. Okay, you can model concurrency contract in this way. And now the happens before relationship between events can be modeled among these 5 types of events. For example, A happens before B if A and B are from the same thread, and A occurs before B. A is the send, and B is the corresponding receive. A is the release, and B is the next acquire on the same lock. And this happens before relationship is transitively closed. And then to detect this race, your criterion is 2 conflicting memory accesses are raised if there's no happens before between each other. And to define redundant events, we imagine we have a happens before algorithm. We call it happen race detector, and this will take an event string as input. The event string is during execution the events you observed so far. Okay, so there are 2 possible outputs of this algorithm. One is you haven't detected any race, which is empty here, epsilon, or you detect a race. This race is represented by L1, which is the location of the first event, A1, which is the access type. It can be a read or write, and then L2, A2, similarly. So then we can define an event E is redundant if the results of the algorithm taking a trace tau is the same as the result of the same algorithm taking the trace tau excluding the event E. Here comes our first theorem. 2 events, A and B, are concurrentially equivalent if we have 3 conditions. The first 2 are very trivial. A and B from the same program location with the same access type. The second, A and B access the same dynamic memory location, which you can check easily, efficiently at runtime. The third one is the most interesting one. It basically says A and B have the same inter-thread happens before relation. In other words, for any event E that is different from the thread of T1 or of TA or the thread of TB, you have such a relationship. So if E happens before A, then you will have this E must happen before B. And if A happens before E, then B must happen before E. And you have this bidirectional relationship. With these 3 conditions satisfied, then we have this theorem. An event is redundant if there already exists 1 concurrential equivalent event from the same thread or 2 from different threads, regardless of the event in the future execution. Basically, it says, hey, if there already exists 1 event that is concurrentially equivalent to the current event, that event is from the same thread, or there exist 2 concurrentially equivalent events from the current event from 2 different threads, then you can safely drop the current event. By dropping that, it's sound, which means that you don't need to care about any possible future events. No matter what possible future event it is safe to drop it. So this is the first theorem we have. The second one is we want to ask this question: what's the optimal condition to drop events? You can keep dropping, but what's the best you can do? That so that when you drop this event, you will affect the risk detection result. So then we introduce something called concurrentially subsumed condition. Specifically, an event B is concurrentially subsumed by event A if 3 conditions. Okay? The first 2 are the same as before. The third one is different, which the only difference is now the arrow is not bidirectional, it's just one direction. Meaning that if for any event E that's different from the thread TA or 2B, and if E happens for A, then E must happen before B. And if A must happen before E, then B must happen before E. So you say B is concurrentially subsumed by event A. Okay? And then the Serum says an event is redundant if there already exists one concurrential subsumed event from the same thread or 2 from different threads. Okay? Meaning that you can keep dropping the redundant events until you don't find any concurrentially subsumed. And why this is optimal? When you don't find any more concurrentially equivalent events, you cannot keep moving it, and so that's it. Otherwise, a unique race may be released or may be missed. The reason is a race must contain 2 events from different threads. That's why we have that condition. And here, there's one thing I want to clarify. By optimal, we mean we are talking about concurrential equivalency in this big context. Okay, so meaning that we cannot further remove any concurrentially equivalent events. But it is still possible to further remove events from the remaining trace without affecting the risk detection result. But to do that soundly, it would require checking happens for relation between events, which would be expensive. So, so the key benefit of our criterion is that we are able to drop events soundly without checking happens before relation. So we develop an online algorithm we call REX, which can check the concurrential subsumed equivalency condition in a very simple way, because checking only the event attributes against some simple conditions, the 3 conditions, and there's no need to check happens for relation between events. So we have to define 2 additional concepts. One we call concurrency context. The second is concurrency history. But concurrency context, basically we say, under this concurrency context, if you have 2 events, okay, and then you may be able to drop some events. Okay? So the history of the concurrency context of an event, of a thread regarding the current event is the history of send and release events observed by a thread T. Here, why send and release? Why not the other 3 types of events? Here's the interesting part, because only send and release introduces outgoing happens before ages, which is actually related to the concurrential subsumed condition. And for all the others, they can be simply ignored because they don't introduce outgoing happens for inter-thread happens for ages. And then we can union all the concurrency context of thread T in the data structure we call try to check the redundant events efficient runtime. So we can discover an event if the concurrency history respect to a program location contains a concurrency context with 1 event from the same thread or 2 from different threads. So this is basically what our conclusion is. Here an example. So this is a slightly more complicated example. You have multiple threads, and then you have log statement, you have read and write, fork. So from this, suppose you observe a trace like that. So the trace includes the 5 types of events with the attributes. By checking the event attributes only, without any happens for relationship, we can built a try data structure, which basically take an event and check the event attribute and look for entries in the try. For example, each node is actually associated with the stack, and this stack has only 2 entries, which basically says, hey, this is the capacity you have. If you have more than 2 events that can fit into the stack, then you should drop this event. Okay, for example, for the event E27, you can safely drop it. So that's the redundant event. Okay, and why we use this try data structure? Because in practice, the concurrency context, because this is a stack-based execution model, so the concurrency context typically exhibits strong locality. The try leads to compact storage of the concurrency history and fast retrieval of stacks. And here is the basic algorithm. Here's one more thing I want to mention. So when you are maintaining this try data structure, multiple threads can access this try. So in order to ensure the soundness and the correctness or optimality, you have to synchronize the try data structure. Especially in this case, you given this concurrency history with respect to program location, given the current concurrency context, you want to get the stack. In this case, you have to synchronize. But synchronization across multiple threads is very expensive. Okay, that's why we drop this synchronization. We basically completely remove the synchronization on the try. This will not produce an optimal result, but it can ensure the soundness. In other words, thread may concurrently create stacks which will lead to missing redundant events, but non-redundant events will never be misclassified. And we also, in our paper, we also have this Lockset-based optimization. So this is also a very nice optimization, but one thing I want to mention is this is unsound that happens before because of Lockset conditions, but it is sound for Lockset-based algorithm. So with this Lockset optimization, you are able to drop more events, but in general, this is not sound. So we evaluated based on the Roadrunner framework, which is Java implementation, which is based on bytecode rewriting to generate events. So basically, we disabled all optimization. So our technique, Rex, is as a pre-filter of the event string generated by Roadrunner to fast track. So we compare the performance between and the risk detection results between fast track with and without our technique. So we run it on both Java Grandie benchmarks and Decouple benchmarks. Here's a hardware configuration. So in summary, we found over 99% of all the events in this programs are memory access events, reads and writes. And overall, 90% of redundant events can be identified by our algorithm, and the runtime performance improvement is around 30%. And the memory overhead is actually not very large. It's only 1.3 times memory overhead compared to fast track without redundant technique. And also, we hypothetically evaluated the optimal performance. Imagine we don't have any redundant events from the trace. What's the optimal we can do? So we calculate the optimal runtime performance in this way. X minus y plus z times 1 minus the percentage redundant event. So X is the cost of our technique plus fast track, which we can measure directly. And Y is the cost of our technique alone. And Z is instrumentation cost of all events. You have to do instrumentation. For example, Z, if you use hardware, Z will be very, very small. But since this is based on software-based rewriting, so Z is actually large in practice. And redundancy is the percentage of redundant events which we have. So under this, we can calculate that if all these are removed without any runtime cost, the fast track performance could be potentially improved by 90% on average. And for most benchmarks, there were some worst case scenarios. If we exclude those worst case scenarios, most fast track runtime overhead could be reduced by 95%. And also, we measured the number of detected total and unique races to basically empirically validate our technique is sound or not. So we found that our technique with and without Lockset produce the same unique data races. That's important. We produce the unique data races. And also, we found that the error output verbosity is greatly reduced because the same amount of some number of unique data races are reported, but the total number of races is greatly reduced. Okay, I think I can stop here. So a summary, this is, to our best knowledge, is this the first study of race detection performance from the perspective of redundancy. We really want to emphasize the concept of redundancy here. And we introduce a criterion, concurrential redundancy, to characterize such redundant events. And we also propose a generalized online algorithm, REX, to efficiently remove such redundant events. And our evaluation shows in practice can be fast track performance can be improved by 30%. I'll stop here. Thank you. I'm happy to take questions.
Hi. So I've been confused trying to read your paper. And in your talk, you say the overhead of fast track is 68x, but the original fast track paper had an overhead of about 8.5x. That's a huge difference. That's almost an order of magnitude. Can you explain what's going on there?
So I think original fast track tool, because this is implemented based on the Roadrunner framework. So Roadrunner itself has many optimizations. So for example, there are some unsound optimization. I think it's called slow pass. I forgot the name of that. There was some optimization we disabled because we wanted to study this question. Suppose a full event string is generated, and then how fast track would be. So that's one difference. I think a second difference is I think we run more threads. To measure the runtime overhead. In this case, for 68 runtime overhead, that was for Java Grande benchmark, which is CPUs intensive, and we included 20 threads for each thread.
So it sounds to me like you're comparing against kind of a critically broken or de-optimized version of fast track. And that's what you're getting performance improvements with respect to. And I think it would really strengthen this work if you went back and compared and empirically did the same experiment against the regular version of fast track. I think you might get very different results. It would be great for the community to see those results too. Thank you.
Thank you. Thank you.
Can you comment on how this could potentially be combined with the technique we saw in AI? Is there anything that prevents
So that's a very good question. So firstly, I think so you putting multiple events together to turn it into a single event, that's a very interesting idea. So I think if we can generalize that without static analysis, that will significantly improve the practicality of this technique. And so far, it sounds natural to combine the current Bigfoot with this runtime technique because Bigfoot is static analysis and this is dynamic analysis. Okay, but I think there are some difficulties on defining what is redundancy when taking the multiple coalesced accesses into single one when we are checking redundancy with a runtime technique. So that may be challenging too.
Bystander here. So I'm not involved in any way in this work, but is it possible, given the big differences that we see between the one and the other, to somehow, create virtual books or something like that, show the benchmarks so that people can see why the differences are so big.
So can
It's not a, it's just a suggestion. It's not a question. It might be good to actually be able to, for somebody else to try to see what the reason for the big discrepancy between one set of numbers and the other one.
So your point is on why this difference between the data reported by fast track paper and
Way to actually resolve this. That's the point.
maybe we can take this offline. Okay, thank you for your question.